Let's take a look at exponential decay now. In this particular problem, we have a very well-known radioactive substance called carbon-14, which we're not going to get into the chemistry of this. We're just going to do the mathematics. This substance has a half-life of 5,730 years. Don't worry, we'll talk about what half-life is. If we assume that we start with 22 grams of the substance, write a function that models the mass of this substance as it decays. Okay, so first let's discuss half-life. So let me change the size of my font here so it's not too big. The half-life of a substance is an amount of time, okay? It's just a time unit. Some people get confused by it. It's just a measure of time. In particular, it's the amount of time it takes for the substance's mass to reduce by 1/2. So, for example, the half-life of this substance is 5,730 years. So if we start with some mass here, we have some starting mass, and 5,730 years elapses, then the mass after that amount of time will be half of what we started with. So in this particular case, we start with 22 grams of carbon-14. This long period of time passes, which is namely the half-life, so at the end of that time frame we only have 11 grams. It cuts in half exactly, and you can imagine that this pattern continues forever. So let's look at another time period here. Say we have another 5,730 years passing, then the 11 grams would cut in half and become 5.5 grams. And this is exactly what exponential decay does. It cuts by the same amount every certain period of time. So half-life is a good measure here. It's a very common way to measure things in science. So I think we understand what half-life is now. Let's work this problem, and in particular I'll use my chart that I have here to help us. I know that the model that I'm looking for, the function that will model this behavior, is an exponential model. So it's f of t equals f sub 0 times e to the kt. So some things I know, since I'm decaying, I know that my constant k will be a negative number. We don't know what it is yet, but it will be a negative number. We also know that our starting mass is 22 grams. So our starting value here is 22. So now the function, these values for f, will be masses. These will each be a mass. So they'll measure grams. The mass after a certain time period is what f of t is. Now, what is the time period? The time period is the time that elapsed, which would be 5,730 years. So that's what we could plug in for time. And after that amount of time passes, our new mass is 11. So that's going to be our f of t. So our f's are masses. F sub 0 is the starting mass. F of t is a mass after a certain period of time, t, which in this case is 5,730. So let's plug all of those things in, and we'll determine the unknown constant here, k, and then we can write our model back out with f sub 0 and k put in, with the true variables being t and f of t in this particular function. So I've cleaned this up. We're going to say 11 equals 22 times e to the unknown value k times t, which is 5,730. Since the variable is in the exponent, we will have to take a log of both sides eventually, but first we need to isolate this guy so we can take a log of it to get the variable down. So to do that, I'll divide both sides by 22, And on the left side, I could leave it as 11 over 22, and there's absolutely nothing wrong with that. However, I can tell that that reduces to a half, so I'm going to go ahead and reduce it since it's so simple. On the right side, I have e to the k times 5,730, which is more commonly written as 5,730k. Now to get the variable out of the exponent, I'll take a natural log of both sides. I could use any log that I want, but since this is base e especially, I'm going to choose the natural log. So I get the natural log of 1/2 equals the natural log of e to the 5,730k. And since I have a natural log base e and an exponential in base e, they're going to cancel out to leave just 5,730k on the right side. And on the left side, I still have the natural log of 1/2. Finally, divide both sides by 5,730. And I can see that k equals the natural log of 1/2 over 5,730. And we could leave it like that. However, in the model it could be difficult to use. So I'm going to go to a calculator and get an approximate value of this. I've entered into Google here, and I can see that I get negative 0.00012, let's say 1210. I'm going to go with like 4 digits after my zeros stop here. So 1210. Negative 0.0001210. Now I can fill in my k value to my model that exhibits the decay of the substance, the decay of the mass. So the model would be f of t, my function, equals the starting mass, which we assumed began with 22 grams. So 22 times e to the k, which is negative 0.0001210, times the independent variable t. And that's the model we can use now to learn much more about carbon-14. Let's take a look at a question that we could answer using this model. Okay, so we want to use this model now to determine how long it would take for 73% of the mass to decay. This is kind of a tricky question for a lot of people. One thing we know is that our starting mass is 22 grams. We need to know this mass after a certain period of time. Now, time is the unknown here. The question is how long. So time is the unknown. Sorry, let me move that arrow here so I'm not covering the variable up. How long means what's the time, meaning I have to know this number, because then that would mean that I could solve for time. So I have to know my mass. Well, the problem doesn't state the actual mass, because mass is measured in grams, right? And this problem never mentions grams. So how many grams are there if 73% of it decays? So 73% of 22 grams is 16.06 grams. So that's how much decays. This is the mass that's left, which means that if I take 16.06 away from 22, I get 5.94 grams remaining. Okay? So I have, here's a picture of it if you want. Oops. I start with 22 grams, and 73% of the mass decays, which means I'm left with 5.94 grams. The question is, what's the time that it takes for this to happen? Well, let's try to solve that problem. So this is going to be our f of t that we'll plug in, and then we need to figure out t. Alright, so let's get started. So we'll put 5.94 in for f of t. So we have 5.94 equals 22 times e to the negative 0.0001210 t, which is our unknown. Since the variable is in the exponent, we'll have to go about pulling it out of the exponent by eventually using a log. Before we do that, we'll divide both sides by 22. So on the left side we have 5.94 divided by 22, and on the right side I have e to the negative 0.0001210t. Now I can take the natural log of both sides, which again is very natural, if you will, because this is base e. So I've got the natural log of the fraction equals the natural log of this exponential expression. And on the right side, the natural log and the base e cancel, leaving behind just negative 0.0001210t. And on the left side, I've got the natural log of the fraction still. Finally, to get t by itself, since that's what I'm trying to solve for, I'll divide by this decimal. So t equals the natural log of the fraction divided by the decimal. And let's put that into Google and see what we get. And it looks like we get approximately 10,820 years. Time in this problem, remember, is measured in years. We know that because, remember, the initial problem, the half-life was measured in years as well. So it takes 10,820 years for 73% of the mass to decay. Now that's true. This number is true no matter what your beginning mass is. You don't have to use 22 with this specific model we did, because we said that was our starting mass. But it would take this long for 73% of the mass to decay no matter what you start with. So if you used 100 for your starting mass and then 27 for your ending mass, if you will, you would get the same time. Now, the reason you'd use 27 is because if you start with 100 and 73% decays, then you'd be left with 27. So try that out and see if you get the same answer. You should. And so that's one thing about exponential models, is when you look at a starting and an ending value, the percentage is the same for the same amount of time, no matter what your starting value is. Okay, hope I didn't confuse you with that last part. It's no big deal. If you didn't get it, don't worry about it. This example should get you pretty far on exponential decay problems.